Hello again. Today we will be talking about some necessarily linear algebra background for data exploration. Previously, we spoke about data matrices. In these kinds of matrices, each row represents an observation, which is actually a vector of features or measurements pertaining to such an observation. Recall that such vectors of measurements can also be thought of as locations in coordinate space. And further, they can be thought of as vectors that originate at 0, 0, or the origin, and go out to the location pointed to by the coordinates of the vector. Matrices can also encode transformations of such vectors. Specifically, they are linear transformations. They transform vectors, for example, by changing their length from the origin or their angle from the x-axis. Here's an example of a stretching matrix. This is a fairly simple linear transformation that stretches a vector by a factor of k. So here you see application of the stretching on the vector 1, 1, stretched it out to 3, 3. So this would be an example of k equals 3. A linear transformation is applied to a vector by matrix multiplication. So the first coordinate is given by k times x plus 0 times y. The second coordinate is given by 0 times x plus k times y. A second example is a rotation matrix. A rotation matrix rotates a vector counterclockwise by an angle of theta. When this matrix is applied to a vector, it results in this formula, which comes from the trigonometric formula for angle summation. So you see that here, the vector x was taken from x to a times x, which simply rotated it and did not change its magnitude. In this example, the vector 1, 0 is rotated by an angle of pi over 4 or 45 degrees. This third example is that of a shearing matrix. This matrix is shearing in one particular direction. What that means is the vectors are stretched in the x direction by an amount proportional to their y value. So here, when you apply this matrix to a vector, you get x plus a factor of m times y, but the y-coordinate is left unchanged. So if you apply this vector, for example, to 1, 1, you get 3, 1. If, on the other hand, if you apply this vector to 1, 0, what happens? It leaves the vector unchanged. That is an example of an eigenvector. Eigenvectors are vectors that are only stretched and not rotated by a linear transformation. Stretching a vector is equivalent to simply multiplying its coordinates by a scalar, as you saw in the example of the stretching matrix. So eigenvectors are actually defined as vectors that satisfy this equation. A times x equals lambda times x, where lambda is a scalar, and in particular, lambda is called the eigenvalue, or characteristic value. This comes from eigen, which is a German word meaning own or characteristic. Eigenvectors give very important information about linear transformations. Linear transformations can be characterized by their invariant spaces, or vectors that they leave unchanged but for scaling. For example, in a 3D rotation, eigenvectors can give you the axis of rotation. For example, if you have a rotation around the z-axis, then any vector that points directly in this z direction is unchanged, and therefore it gives you this direction as the axis of rotation. Certain matrices can actually be eigendecomposed, or decomposed into a product of eigenvectors, a diagonal matrix of eigenvalues, and the inverse of their eigenvectors. This is equivalent to changing the matrix to an eigenbasis and then simply stretching in that eigenbasis and then changing back. And this kind of operation of eigendecomposition can be very useful, for example, in PCA, which we'll see in a future lecture.